to move on to the final talk of this session. Abdullahi, who is speaking to us very late. I believe it's almost 1 o'clock in the morning there.
Yes,
he's at the Donders Institute over in the Netherlands. So please, Abdullahi, go ahead and tell us what you tell us.
Yeah. Well, sorry, just a second. Try to share the screen. All right, I think you can see it.
Yep, looks fine.
Somebody can confirm. Perfect. Do you also see my cursor?
You can, yep.
Okay, that's fine. Then I'll just start. All right. Yeah, thank you. Thank you all for tuning in. I'm going to talk about a project that I've been working on for a while now on the relationship between predictive coding and energy efficiency. As you may know, in neuroscience, the predictive coding framework has arisen as sort of a prominent and very powerful theory of neural information processing. It postulates that there is some hierarchical generative model in our brain that continuously inhibits predictable sensory input. And it does so. It also comes with a few sets of assumptions that, for example, that there are distinct types of cell types in the brain, such as prediction neurons and error neurons, and that these also interact with some specific connectivity motive to implement the information flow of predictive coding. So there are a lot of assumptions there, and these are also typically implemented in computational models of predictive coding, but they are generally hardwired. So a popular one you can see here on the right, it's PredNet. Some of you are probably familiar with it, but this hardwiring is typically is baked in computational models of predictive coding. So you can also ask another question. So where does this architecture exactly come from? And that is what we were interested in this work. So can we potentially explain predictive coding through other, maybe simpler mechanisms? And we think that we can do this. And in this work, we show in a specific setting that when you minimize for energy, you can get the sort of architectural hallmarks of predictive coding to emerge. So how did we do that? So there's a lot going on in this on this slide, and I unfortunately don't have a cursor or a laser pointer to get you through it, but I'll try to do my best by being as expressive as possible. So we feed in sequences of MNIST digits in ascending order. So what does that mean? If you look on the left, you see 6 as the starting digit of the sequence. So after a 6 comes a 7, then an 8, then a 9, then we go to 0 because we have wraparound, etc., etc., etc. If you move then to the network, each unit in the network is connected to exactly one input pixel. And each unit is then connected to all the other units in the network. And of course, we have to make sure that the network can't just trivially turn off its input weights to achieve zero activity or energy. So we fix the input weights. If we then look at a specific unit, the output of that unit is going to be its input drive, which you see on the right in yellow, and its recurrent contributions from the units, from the other units in the network, which we denote as the internal drive. Push that through a ReLU, and then you get the output of the unit. So there is no overarching task. That is a question that I often ask. So what is the exact task that the network is supposed to solve? The only thing that we do is we push sequences of MNIST digits. Those will cause activity, and the objective is to minimize that energy. And so that essentially is the task, and there's no additional tasks where there has to be classification or anything else. So I've already mentioned energy, I think, a couple of times. And what do I exactly mean with that? So in this work, we take the mean absolute preactivation. You can see the mathematical form here on the right. So in the preprint of this work, we show that this loss correlates pretty well with action potentials and synaptic transmission, which are often noted as the two biggest sources of metabolic demands in the brain. And you can see a nice pie chart here on the left to drive that point home. So the first thing that we had to check is whether the network is able to predict its incoming pixel activity. And since the network has a nice topographical correspondence with the input, recall that the each unit is connected to exactly one input pixel, we can easily visualize that in the MNIST case. And you can see this visualization here on the slide. So excitatory, so the red here means excitatory and the blue here means inhibitory. And as you can see, the internal drive here is able to counteract the input drive by not exactly mimicking the shape of the input, but by predicting what is essentially a median digit. And this median digit, which is essentially the pixel-wise median for that digit class, is the sort of optimal solution given this loss function. In addition to that, you might notice that there are some red dots in the internal drive, and these are units that have positive internal drive, which is interesting. Could this potentially be distinct populations, and could these essentially two distinct populations be the functionally correspond to the prediction and error units that that are sort of postulated in the predictive coding framework? That is what we tried to find out next. So if the network would reorganize into two distinct populations of prediction error units, we would expect them to have different properties. And in particular, in this setting, we would expect them to have differences in their median pre-activations. So the reasoning behind this is that if, say that we have a unit that has a bias away from zero pre-activation, well, it essentially must mean that this unit has a functional role in driving down the activity of the network. Since if that wouldn't be the case, the network would just turn off that unit because to reduce the loss. So we use that to identify candidate prediction units. So what we did is we recorded for each class the median pre-activation and constructed confidence intervals. And then we made a decision rule that essentially says if for a particular class that unit's 99% confidence interval does not cross zero, then we identify it as a prediction unit. And here on the slide, you can see an example of that for the digit class 9. So on the right, you can see a decision boundary, and you see that two units have crossed the decision boundary. Up until now, I only have shown you how to identify these units, but I haven't shown you, I haven't demonstrated to you that these units actually play a causal role in the prediction in the network. So that's what we try to figure out next. So to figure out whether these candidate prediction units actually play a causal role in prediction, we did a virtual lesion study. On the left side, you can see a visualization of that. So what you see here is we visualize the energy consumption, which is the pre-activation over time. And each line here essentially denotes a multiple network instances for bootstrapping, and they are averaged over multiple sequence presentations. So we have three situations here. The red line here denotes the normally operating networks, and the green line is a control where we lesion a randomly selected set of what we then call error units, postulated error units, to make sure that the effects that we might see in a lesion is unique to the prediction units. So we're going to focus first on those, on the red line and the green line. As you can see, these networks are able to reduce their energy consumption over time, meaning that they are able to functionally, essentially predict their input, because the only way that you can reduce the energy consumption in this problem is by being able to anticipate what your input drive is going to be. Which also means that lesioning these error units, postulated error units, doesn't seem to have a effect or a deterioration on the prediction. So you also see here a yellow line, which represents the case where we lesion the candidate prediction units. And here you see now that the network isn't able to reduce its energy consumption over time as well, compared to the other two cases that we just discussed, which implies that these candidate units seem to play a causal role in the prediction. In panel B, you see the same thing, but represented in a different way. So if we look at the top row, you can see predictions of the digit class 0 at different times in the sequence. And as you would expect, the further along in the sequence, the better the prediction is, because the network has seen more of the sequence. On the bottom row, you can see a visualization with a network with lesion prediction units. And there you can see that the predictions don't improve, but they also are not completely destroyed. So this implies that there might be two different mechanisms of predictions maybe going on. One faster predictive inhibitory loop within error units when the prediction units haven't had time to integrate information yet, and a slower predictive loop that is mediated by prediction units. So to sum up this slides, knocking out these prediction units deteriorates the predictions, but they are not completely destroyed. To add to these results, it is also important to want to have some form of replication, since as you've already seen, the minimise input is pretty particular, with drive in the center and no drive in the periphery. So we also looked at C410, and we saw similar phenomena unfold in that data set as well. So again, as you can see in panel B, we can sort of identify these, let's say, candidate predictive units, and lesioning these prediction units, as you can see in C, leads to increased network activity, which implies that they have some functional role again in prediction. So to sum up, we are able to, via energy efficiency, to sort of recover hallmarks of the predictive coding architecture, such as functionally distinct populations, and even maybe some form of rudimentary hierarchy. In addition to that, these populations functionally map well on prediction and error units, which is nice to see. So in this instance, we can somewhat conclude that predictive coding, or at least sort of the entire architectural package that comes with predictive coding, might be a consequence of energy efficiency. If you're interested in this work, we have a preprint of this work on bioRxiv. You can scan the QR code here on the right. And thank you for listening. I also want to thank my collaborators. And if you want to contact me and discuss me after this, I'm on Twitter, and you can always send me an email. And I'm also happy to take questions. Thank you.
Great, thanks. That was great. Can you go ahead and unshare the screen? Oh no, actually, yeah, there you go. Perfect. So we got a few minutes before the next session begins. Let me get to, first of all, Kyle Johnson's question, who asks, these prediction units had receptive fields, but just in unimportant areas.
So do you mean yeah, so so in the MNIST case, the prediction units all emerge in the periphery where there is no input drive. So yeah, there are receptive fields there with respect to the input is going to be meaningless, but that also makes them stable, which also might imply be the reason why the network recruits these units to become the postulating predictive units. Yeah.
I had another question, which was that it would seem as if the loss function was just trying to minimize energy, wouldn't it predict that basically it would drive all the synapses to zero?
Yeah.
Is
So
there something to do to sort of prevent that from being a
yeah,
trivial?
yeah. So that would happen if the input weight would be plastic.
Okay.
So we fixed that to make sure, because so the problem statement is essentially there's going to be drive, and you need to be able to adequately deal with that drive.
Mhm.
And for that, we have to freeze those weights. But in essence, I feel like this is a situation that translates, I guess, to its well to a circuit in the brain, because we can't just close our eyes and sit somewhere. We have to actually engage with the information stream. So in that essence, I think this is okay. But yeah, it's sort of a hard code trick to deal with that. Yeah.
Right. And I can see how that would work for a one-layer deep system, but then I wonder if you had multiple layers, right?
Yeah.
You can't force these guys. You can't force everything up to this current layer to be fixed. Like they've all got to be plastic all the way
Yeah.
down the line.
Yeah.
Um,
That's true. And that definitely would be the next step. So in essence, at some point you have to. So at some point So the problem is, I think the solution there would be if these higher order layers can learn something useful that you wouldn't get if you just have a shallow network, then naturally the network would recruit them. So it's all about like a trade-off, right? So how much does it cost to have these circuits to be active, and how
mhm,
much do they actually give
mhm.
you to solve the problem?
Right,
So it
right.
will probably be something like that. That's definitely a
Some
way.
kind of value function for what's the utility of these weights not being zero.
Yeah.
Right.
Like if they're super expensive and they don't give you any like functional gain, then obviously you don't want them to be on. But if like having this like additional latent structure gives you like a better solution to, for example, minimize energy, then the network will probably opt into
Mhm.
using those structures. Yeah.
All right. Well, we are out of time here. Thank you very much for those three very interesting talks.